Okay, so we've already discovered that an object in simple harmonic motion, an object oscillating back and forth um, with a relatively simple mathematical function describing it, and that mathematical function is a cosine. Okay, we discovered that in multiple ways, some of which were these nice examples of, again, the spray paint can oscillating up and down, and we saw that the pattern it makes is that of a sine or cosine curve. Right? We also talked about other ways in which we solved the differential equation and found that cosine and sine is a good solution for that differential equation. So again, if I want to describe the motion of this object oscillating back and forth, one good way to do that is that the position of this object as a function of time is equal to the cosine of the time. Right? And that's going to help us describe this motion. Okay, so let's try to learn more about this equation and try to develop it a little further to handle any situation by talking through it with a couple of clicker questions. All right, so we have this equation that describes this oscillator as a function of time. So at time equals 0, if the box is at its max amplitude of x equals 1 meter, at what time does it return to x equals 1 meter again? So how much time does it take for this oscillator to go to here and all the way back to here? And that's if its position as a function of time is described by this equation. So take a moment and think about that, and when you're ready, you can move on to the next slide, and we will discuss the answer. But again, think about how long does it take for a cosine to return back to its original position. Okay. So the answer here is D. This box is going to return back to its original position 2 pi seconds later. How do we know that? I know that at its maximum position at x equals 1 meter, it must be that cosine of 0 is equal to 1 meter. Okay, so that's good. Cosine of 1 is equal to 0. I'm sorry, cosine of 0 is equal to 1, excuse me. But I also know that cosine of 2 pi is equal to 1. I also know that cosine of 4 pi is equal to 1. I also know that cosine of 6 pi is equal to 1. So it appears that every 2 pi seconds, this box is going to return back to its original position. All right, so the period in this case is just equal to 2 pi. Okay, and so I could plot this equation, x of t as a function, I'm sorry, position as a function of time is equal to cosine of time. And when I do that, I get this curve, where originally at time equals 0, I'm at x equals 1, right? I'm at my max amplitude. And then the time for one complete cycle is a little over 6 seconds, or 2 pi seconds. Right? So we can see that if this time is 2 pi seconds, that's how long it takes me to get back to my original position. Okay. If I know this equation, what is the period of this oscillation? Well, I think I already gave away the answer to this. The period is equal to 2 pi. All right, the period is how long does it take to go through one complete cycle, one complete oscillation. Okay, so I can tell directly from this formula the period. Even though 2 pi doesn't appear in this formula, I can, since I know how a cosine works, I can figure out from this formula what the period is. Okay, what if I did this? What if I said this was the equation, x is equal to 2 cosine of t? What is the period of this oscillation? Okay, moving to the next slide, the answer is still 2 pi. Right, so if I multiply my equation by 2, the position is now described by 2 cosine of t. I am not affecting the period. Now it's oscillating back and forth between x equals 2 meters and x equals minus 2 meters instead of x equals 1 and x equals minus 1 meters, but it takes the same amount of time to go through one complete period. Right? In both cases here, it takes 2 pi seconds to go through one complete period. Okay, so we know that. That has to be the case. That's what makes a simple harmonic motion. Okay, if I told you this equation, could you tell me the amplitude of the oscillation? So think about that one and then move on to the next slide. And the answer here is C, or 2 meters. And again, we saw this already. So whatever number is out in front of this cosine function is going to tell me the amplitude. Right? 2 times cosine, well, the biggest cosine can be is 1. Right? Cosine of 0, cosine of 2 pi is equal to 1. So if I just multiply 1 by some number, that tells me the actual position at that moment. When cosine is equal to 1, the position is equal to 2. Right? So that 2 is telling me the max amplitude. So this object is oscillating back and forth between 2 and minus 2. Okay, so just a summary of what we learned. we started with this equation, and we know that the position is being described mathematically by a cosine, and we know that whatever number is out in front is the amplitude. So again, if the equation is x equals 5 cosine of t, this tells me the amplitude is 5. Okay, whatever number is up there. It's oscillating back and forth between x equals 5 meters, or when cosine is equal to -1, that's the smallest cosine can be. That tells me the position is equal to -5 meters. Okay, so we've somewhat expanded our equation, right? We can now not only describe something oscillating back and forth between 1 and -1, we can now describe something oscillating back and forth between any position and any other position. Okay? Let's keep trying to expand this equation. What if I, instead of multiplying a number out front, what if I multiplied t by 2? What if I did x equals cosine of 2 times t? What if I put 2 inside that function? Now, what is the period of this oscillation? So pause the video. This one may take you a little bit more time to think about, but you can make the same argument we did in the first equation, in the first question in this video. Okay, so the answer here is C. Okay, the period is now pi seconds, so it now takes pi seconds to go through one complete oscillation. And so by multiplying t by 2, I've basically shrunk down my cosine. If I plot my green curve here, that is x equals cosine of t. If I do x equals cosine of 2t, I now go through 2 complete oscillations in the period before, where I went through 1 complete oscillation. So before, my period was 2 pi, now my period is just pi. It takes pi seconds to go through 1 complete cycle. Okay, and we can check that again with this basic knowledge of how cosine works. Cosine of 0 is equal to 1, cosine of 2 pi is equal to 1, cosine of 4 pi is equal to 1. So if it's cosine of 2 times t, this is going to be equal to 1 when t is equal to 0. It's going to be equal to 1 again when t is equal to pi. Right? So that tells me that the period is equal to pi. Okay. What about this equation? What if I did cosine of 2 pi times t? What is the period of this oscillation? So take a moment and think about this. Okay, and the answer here is A. Right? By the same argument, that cosine of 0 is equal to 1, cosine of 2 pi is equal to 1. Now I plug in 0 here, that's where I start at time equals 0. And then when does this get back to its original position? When does this get back to x equals 1 again? When I plug in time equals 1 second, because cosine of 2 pi is equal to 1. So that tells me I'm back to my original position. So now if I plot cosine of t, again, that's this green curve where the period is 2 pi seconds. But if I plot x equals cosine of 2 pi times t, you can see it's now oscillating really fast, and it takes exactly 1 second, right, 1 second on the x-axis here, 1 second to go through 1 complete oscillation. Okay, and what is the frequency of this oscillation? So think about that for a moment. The answer here is 1 per second. Okay, we know that frequency is related to period. If the period is 1 second, it takes 1 second to go through 1 complete cycle. That means it's also oscillating once per second. Okay, so relating frequency and period is relatively easy. Okay. Now what about this equation? Consider the equation 4, cosine of 4 times 2 pi times t. Pause the video, think about what is the frequency of this oscillation. And when you do that, you plug in, and this takes a little bit of thought, but let's see what happens here. X is equal to cosine of 4 times 2 pi, and if I plug in half a second here, I get cosine of 2 pi, right? 4 times 2 pi multiplied by a quarter, well, the quarter just cancels out that 4, so I get cosine of 2 pi is equal to 1. So I can figure out the amount of the period, or the amount of time it takes for this object to go through 1 complete oscillation is 0.25 seconds. Okay, and so once I know that, that tells me the frequency is equal to 4 per second, right? 1 over the period is 1 over a quarter is 4. Okay, so I can see again here I'm plotting x is equal to 2 pi times t, where the period is equal to 1 second. If I instead do cosine of 8 pi times t, it's oscillating faster. The period is now a quarter. right? And so in 1 second, it's going through 4 complete oscillations. Okay, but you'll see that if we wanted to write down an equation to describe something that has an oscillation frequency of 4 per second, this would be a nice way to write it down, right? So that the 4 is very explicit. 4 times 2 pi times t. I could immediately look at this equation and figure out that the frequency is 4. Okay, so that's what we're going to choose to do. Right? If we want to describe something mathematically that oscillates f times per second, we should write it in this way, where x is equal to a, the amplitude, times cosine, times the frequency, times 2 pi, times time. And if you write it in this way, you can just immediately read off that the frequency from this formula. So that would be very nice if you didn't have to do any thinking. You could just look at the formula and read off the frequency. Okay, and we already introduced this concept of angular frequency, which we use the symbol omega for, which is just 2 pi times the frequency. So this is in units of radians per second, where frequency is in units of per second. But you'll see one nice reason we introduce this is once I write things in that way, I can rewrite this formula just like this. X is equal to a cosine of omega t. Okay, so when you're writing down the equation for an oscillator, oscillating back and forth, if you write it down in this way, you can immediately read off the amplitude and you can immediately read off the angular frequency. Once you know the angular frequency, you can always find the frequency using this formula. Okay, and we can just quickly check the units to make sure everything makes sense. We want to know the position in meters. Well, amplitude is measured in meters, and then cosine times frequency, which is per second, right? Cycles per second. Time is in seconds, so whatever is in the bracket here is unitless, and so we just have meters is equal to meters. Okay, same thing here. X is in meters, amplitude is in meters. Omega is radians per second times seconds. Well, that cancels out the seconds. And we know that radians is not really a real unit, so it's really unitless. So still within the bracket is unitless, and we end up with something meters is equal to meters. Okay. Now let's complicate things even more by adding another term to our equation. Right? What if the position was given to cosine of t plus pi over 3? So now instead of multiplying by a number, we're adding a number within the function. What is the period of this oscillation? So take a moment and think about that. Okay, and the answer here is still 2 pi. Right? So by doing this, cosine of t plus pi over 3, I did not change the period. Right? All I did was shift the function back and forth. So the green curve is x equals cosine of t, and the blue curve is x equals cosine of t plus pi over 3. And you can see I just kind of shifted the whole function to the left. Right? The blue curve is just the green curve shifted to the left. But the distance between two peaks, right, since I'm plotting the time, the distance between two peaks is the period. Okay, and so the period hasn't changed when I did this. Okay. Another question. For this equation, what is the position of the mass at time equals 0? So think about that, and on the next slide, I'll give you the answer. Okay, so what is the position at time equals 0? Well, this is a function that tells me the position at all times, so all I have to do is plug in time equals 0, and it tells me the position. Right, so I plug in time equals 0. Time equals 0, I have x is equal to cosine of pi over 3, and so cosine of pi over 3 I know is equal to 1/2, or 0.5. Okay, so the answer here is B. So you'll see what happens here. The advantage of writing the function in this way is that now I can describe an oscillator that at time equals 0 is not at its maximum amplitude. If I was always just using x equals cosine of t or x equal to 5 cosine of t, I could only describe oscillators that at time equals 0 are at the maximum amplitude. But if I add in this term, I can shift this function back and forth, and now I can describe something that at time equals 0 is not at its max amplitude. In fact, it's at x equal half its max amplitude in this particular case. Right? So it's not at x equals pi over 3 initially. You have to plug in pi over 3, and you find that it's initially at x equals 1/2. So this is what we're going to have to do to describe a oscillator which is not at its maximum amplitude initially. Okay, so we started with this equation, x equals a cosine frequency times 2 pi times t. And again, this only describes something which at time equals 0 is equal to at its max amplitude. All right, so if I plug in time equals 0 here, I have cosine of 1. Cosine of 0 is equal to 1. 1 times amplitude, that means the position is just equal to the amplitude. If I take the same equation and I add this extra term in, like in the previous example it was pi over 3, now I can describe something that is not at max amplitude initially. So this thing I'm adding in, we're going to use a simple phi for, and we're going to call that the phase angle or the phase constant. Okay, so two different terms for that. So this extra term phi is the phase. And so when I again make the substitution that omega is equal to 2 pi times frequency, we end up with this equation. This is going to be our general equation to describe anything that's oscillating. Anything that's oscillating in simple harmonic motion can be described with this formula. And that was kind of our goal initially. We want the equation of motion. We want to describe the position of this moment at any moment in time. Okay, and that's what this equation does. So let's look at this in a little bit more detail. Again, let's check how this phasing works. Right. So again, if I plot x equals cosine of t in blue, at time equals 0, I'm at my max amplitude. If I plot x equals cosine of t plus pi over 3, so my phase angle is plus pi over 3, I'm initially at 0.5, and I'm initially moving in the minus x direction, so that's this orange curve. Okay, so that shifted the whole function to the left, right? The blue function shifted to the left to make the orange function, and so it shifted this blue curve over, so it's initially at 1/2. Okay, if I did cosine of t minus pi over 3, right? Cosine of minus pi over 3 is also equal to 1/2. So both of these are initially at the same initial position. X is equal to 1/2 a meter. Okay, but they're describing different oscillations. The green curve is a blue curve shifted to the right, which means we're still rising towards our maximum position. So this describes an oscillator which is still has positive velocity. It's moving towards this maximum amplitude, and then it's going to turn around and start moving the other direction. Right? So we can, by either having a positive phase angle or a negative phase angle, we can shift our function back and forth. Okay, if we picked a different phase angle, example pi over 2, well, if I shift cosine by pi over 2, I just get sine. All right. Well, I'm sorry. If I do a positive phase angle, pi over 2, I get negative sine. Right? If I do cosine of t minus pi over 2, I get positive sine. All right, so this is one of our trig identities. When you shift cosine by pi over 2, you get sine. All right, so that we don't need to use sine to describe an oscillator. We could just use cosine plus a phase angle. So if your oscillator is initially at time equals 0 at its equilibrium point, then you can use a phase angle of pi over 2 radians, right? And finally, I could shift it by pi, and that would just flip things around. So the blue curve is, the red curve is cosine. If I do cosine plus pi, I just get negative cosine, right? So that's that green curve. So if we want to describe something that's initially at its minimum amplitude at x equals minus a, or in this case x equals minus 1, you could just do cosine of t plus pi, okay? A phase angle of pi. And if I use a phase angle of 2 pi, well, that's bringing me back to where I originally was. So the blue and the red are equivalent. All right, so hopefully putting this all together gives us this formula, which is going to be really important for us to describe the motion of something which is oscillating. And if I were to tell you this formula with numbers, right, you should immediately be able to tell me the amplitude, the angular frequency, and the phase angle or phase constant. Okay, thank you.